Good afternoon, everyone. Welcome to the CERN colloquium. Today, we are very happy and very grateful to Professor James Peebles, who is joining us from Princeton. Let me quickly introduce our speaker. Professor Peebles got his PhD from Princeton in 1962, where he stayed ever since, and now is a Professor Emeritus of Science. So James Peebles' theoretical framework, developed since the mid-1960s, is the basis of our contemporary ideas about the universe. The cosmic background radiation is a remaining trace of the formation of the universe, and using his theoretical tools and calculations, James Peebles was able to interpret these traces from the infancy of the universe and discover new physical processes. The results showed us a universe in which just 5% of its context is known matter, and the rest, 95%, is unknown dark matter and dark energy. We will hear more about this, I'm sure, today. And for his work, he shared the Nobel Prize in Physics in 2019 for his theoretical discoveries in physical cosmology. It's a memorable Nobel Prize also here in Geneva, because two other laureates were locals. And this being said, please, Professor Peebles, the floor is yours. Thank you for joining us.
Thank you, Sasha. Colleagues, the theme of this talk will be the observations by a physical scientist of what social scientists, sociologists of science are doing, and concluding about the work of natural scientists who examine the world around us and try to add making sense of what it is all about. If you find this topic interesting, then I offer you a commercial. I offer you, where am I? Now I must start. Is it here? Share. Am I showing it? You know, I never liked Zoom. Is it showing?
We see the keynote, but not the full screen. Yes. There you go.
Well, here is the book that I shamelessly offer for your consideration, available in a bookstore near you, if you happen to have a very good bookstore near you. It discusses the fact that sociologists of science and scientists do not always get along well. I'll give you examples. It also discusses some points in which sociologists of science make a very good point about the nature of our enterprise in natural science. So to begin, I remind you or tell you about the book Laboratory Life by Bruno Latour and Steve Woolgar, late 1980s. Latour immersed himself in a laboratory for research on biological models for 2 years. It's fair to say that when Latour entered this experiment, he knew nothing about the practice of natural science. He was there as a sort of anthropologist, observing a tribe of people of which he had very little knowledge, and trying to deduce from observations what these people were up to. I reproduce here a conclusion from that book. We are not arguing that this spectacularly complicated molecule does not exist, nor that it does not work, but that it cannot jump out of the very framework of social practice which makes possible its existence. That is a wonderfully fine-tuned conclusion. We see an even stronger, and in fact, well, here is the molecule as it is now. I don't know the state of understanding of this molecule in the 1980s, but let us look at another book, The Structure of Scientific Revolutions by Thomas Kuhn, who concludes, there is, I think, no theory-independent way to reconstruct phrases like really there. The notion of a match between ontology of a theory and its real counterpart in nature now seems to me to be elusive in principle. I gather by ontology he means the reality assumed in the theory. he observed that we as people are, of course, influenced by our culture, and that culture inevitably influences the way we look at physics. He is arguing that the way we look at physics is so culturally determined that it's not at all clear that the reality we talk about has a real counterpart, if there is such a thing. Interesting that Kuhn has a PhD in physics under Van Vleck, a Nobel laureate at Harvard. He was quite aware of the successes of physical science, but he dismissed them as problem solving. That is to say, I gather, you decide on a theory and then you solve the problem of making the theory look like the observations. Still earlier, William James, it is as if reality were made of ether atoms or electrons, but we mustn't think so literally. That was one line of thought about us scientists. James was a friend with another person, philosopher, Charles Sanders Smith. Charles was rather an erratic person, and James worked hard to try to get him a permanent position in a university because he was a very capable person. The quote, which I'll read, "One man may investigate the velocity of light by studying the transits of Venus and the aberration of the stars," and so on. He points out, oh, and by the way, I decided to clean this up. Ah, there we are. One may investigate the velocity of light in essentially three different ways. First, it can be measured in the laboratory in those days. It took a lot of skill and mechanical engineering, but it could be done. We could measure the velocity of light by astronomical observations. I mentioned just one example. The orbits of the planet Jupiter are seen to circle the planet and to be moved behind the planet at a very sharply defined time. The time at which a satellite, a moon, moves behind the planet could be well measured and was found to change with time as the distance between the Earth, the Sun, and Jupiter changed as the two planets moved around the Sun. Lengths in the solar system were pretty well known then. First, one had a measured radius of the Earth, and then by trigonometry, distances to the other planets. One then knew that length. You knew the time delay as the lengths changed, so you knew the velocity of light. And finally, people studying electricity and magnetism were coming upon a characteristic number of velocity, the speed of light, as was then speculated and soon to be checked. So he points out the velocity of light is measured by three quite different methods, and one gets the same answer within measurement error. That's surely not what you would expect if the speed of light were just a number made up by a particular culture. Instead, it argues that the velocity of light is a real number, quantity, a characteristic of the world around us. He gets a little over the top as each method perfects. The results will steadily move together toward a destined center. It's an interesting point to me that we all assume that nature operates by laws that we can discover. And that assumption is strongly encouraged by so many advances in science. It was never handed down to us by a higher authority. We were never issued a guarantee that science would work. And I wonder why people are so strongly convinced of it. Well, practice works. Here is another case to consider. James Clerk Maxwell, a century and a half ago, put together lots of experiments in electricity and many in magnetism, made them consistent. And I quote here, the opinion seems to be gotten around that all that's left is to carry on measurements to another place of decimals. I mention this because I learned that in college. I had always assumed that Maxwell had expected that after the great discoveries he had made, there was nothing much left to do except add decimals. But he adds, and I only realized this after I started looking into sociology, We have no right to think thus of the unsearchable riches of creation or of the untried fertility of those fresh minds into which those riches will continue to be poured. The analogy is kind of brutal, but the point is excellent, and it has happened. I also wish to emphasize a point that is manifest and obvious, but yet to some not so apparent. Maxwell's equations have been applied in such an enormous variety of applications. You could list it endlessly. And the success of each of those applications is, to my mind, a test of the theory that the theory passes. That broad range of applications surely is telling us that Maxwell's equations are a good approximation to reality. They're not perfect, of course. It fails on small scales like an atom. And if you want to get technical about it, you may say that Maxwell's equations are wrong. So are all the rest of our physical theories, if you want to get technical about it. But of course, Maxwell's equation looks like a wonderful, good approximation to objective reality. And I assert so it is with all our established physics. And I also assert this is the best we can ever do because we can never demonstrate to arbitrarily good accuracy that the theory matches the predictions, that the predictions match the observations. We can't assert that to indefinite accuracy. So we can't say that we have the final theory. People object to my saying that, but I hold to it. One does wonder whether instead of studying something as complicated as somatostatin, Latour had studied something well established like Maxwell's equations. Would that have convinced him that there is more to this aspect of reality? And I will now point to another aspect of this discussion. Consider the book by Landau and Lifshitz. My copy is the English edition in 1951. There is the frontispiece. The first 2/3 of this book present in wonderful detail the behavior of classical electric and magnetic fields. This is solid stuff. The last third of the book is on Einstein's general theory of relativity. In 1950, when that book was published in English, general relativity, I assert, was a social construction that the elite made a canonical part of physics, even though the three tests were marginal at best. That is because there were the three classical cosmological tests. Although only a few recognized it in 1950, the best test of the gravitational redshift by observations of a white dwarf, I've forgotten its name, but as it happens, the best measurement of the redshift from that white dwarf was off by a factor of 4 for present measurements. And it just happened that the best estimate of the prediction, which depended on the radius, which depended on a good understanding of the properties of degenerate matter, was off by a factor of 4. They happened to agree. Some knew that. It's a pretty shoddy piece of evidence for the theory. The general precession, the anomalous precession of the orbit of Mercury is a successful prediction of general relativity. But if you want to get technical about it again, Einstein stopped looking for improvements to his approximations to general relativity when he got the observed precession of the perihelion of Mercury. There's lots of good reasons he would have stopped even if he hadn't known about that, but still, it kind of taints the test. And so the one last test that worked to maybe 30% accuracy was the deflection of light around the sun. Pretty thin stuff to require, as I experienced, that to pass my general examinations as a graduate student, I had to be prepared to demonstrate an understanding of the elementary aspects of special relativity, the meaning of a line element and such things. The message I send here is that this is an example of physicists dealing with social constructions. We do it all the time. nothing to apologize for. But of course, we notice that general relativity theory now passes wonderfully demanding tests on an enormous range of scales that make it a solid, well-tested scientific construction. Of course, that's now, not then. And let us pause to admire that it became a respectable part of physics because it passed lots of tests. I turn now to another aspect of sociology, what some call multiples in scientific discovery. These two people, William Ogburn, Dorothy Thomas, in 1922, published a list of inventions made by more than one person or group. Here is part of their list. Kinetic theory of gases, good. Law of conservation of energy, lots of people could be credited with that. Mechanical equivalent of heat. I was surprised to see continuity of gaseous and liquid states of matter. That's a pretty subtle thing, but yet two people claim to have it in the late 1800s. Robert Merton, more recently, who was until recently professor of sociology at Columbia University, no longer with us at last, who commented on these multiples in scientific discovery that in fact sociologists had periodically rediscovered the notion of multiples. It is, as he suggested, a Shakespearean play within a play. The sociological construction, this phenomenon is, in my personal experience, quite real. I offer an example to come from the establishment of the relativistic cosmology. I just begin by reminding you of the notion that Einstein introduced in 1917, that in the 1920s, people accepted without a lot of evidence that the universe is uniform, statistically homogeneous, apart from the local clumps, but on average, uniform, the same everywhere. To see what that means, imagine for a moment you live on the surface of a two-dimensional balloon, and you notice that if you walk in one direction and the balloon is not expanding, you will eventually arrive back where you started. Here's a universe that is bounded but has no edges. Now also notice that if this person, Professor Dr. Willem de Sitter, who will later is explaining, imagine someone is blowing up the balloon. Now, I must caution you, the galaxies in the balloon are not expanding apart from ordinary physical effects. You and I are not expanding apart from the usual physical effects. But what it is meant to point out is that the galaxies are moving apart. And furthermore, you will notice if this observer sees this galaxy moving away at a definite speed, then this one that's about twice as far away would be moving away twice as fast. That's Hubble's law. It was discovered. And here, just as a historical note that pleases me, in a reasonably linear way, beginning with Percival Lowell. The Lowells of Boston were of the highest social class and the greatest richness. There is even a poem in celebration of them. So now we are in Boston, the home of the bean and the cod, where the Cabots speak only to Lowells and the Lowells speak only to God. Percival was one of those Lowells. He became fascinated by astronomy and by the notion that there may be civilizations on the planet Mars that may be very advanced, and among their great accomplishments was the construction of canals to carry water all over the planet. That's sociologically understandable because at that time there was a big civil engineering operation of building canals, Suez, Panama. Naturally, it would occur to him that if there's really advanced, they're really building really big canals. Astronomers celebrate Lowell's memory because he built an astronomical observatory in Arizona, Flagstaff, where the seeing is really good, instead of building it as others had done in a place convenient to where they live. And he also hired excellent astronomers to instrument and use his telescope. Among them was Melvin Slipher, who developed the technology to measure spectra of galaxies well enough to see that the spectra are shifted away, most of them as if they were moving away from us, and by the Doppler shift, their wavelengths growing larger. It was Henrietta Leavitt at the Harvard Observatory who taught astronomers how to measure distances to a class of stars with the variable Cepheid variables. And it was Edwin Hubble, I think we can chiefly credit for putting together Slipher's observations and Leavitt's methods to determine that the redshift of a galaxy, its apparent recession velocity, is directly proportional to its distance. Here's an illustration of the situation. You see in the lower left, Hubble's 1929 discovery paper. I'm not so sure that you'd be impressed with this as evidence of a linear relation, but by the year 1936, Hubble and his excellent assistant, Humason, had pushed the redshift distance relation out to log velocity in kilometers per second, 4.5, a tenth of the speed of light. Really a magnificent advance. I'm led to reflect that when I was 1 year old, astronomers had been observing galaxies apparently moving away from us at a tenth the speed of light. And it's also interesting to notice that it took until the turn of the century and more before astronomers could complete the next decade in redshift measurements out to redshifts approaching unity. That's the way science is, isn't it? Sometimes great advances all at once, sometimes very slow advances. Let's just notice that the notion of an expanding universe was hit upon by at least three people: Hermann Weyl, Alexander Friedman in Russia, Hermann Weyl in Germany, and Georges Lemaitre in Belgium. Lemaitre put together, I should say that Weyl didn't have a universe, used the de Sitter solution for a universe with no matter. He really didn't have a theory. Alexander had a solution. He had a theory, a solution to Einstein's field equation, but he didn't know about the redshifts of galaxies. Lemaitre knew both, applied them very clearly, and is best credited to be the discoverer of the law of recession of the galaxies, the notion that the universe is expanding. I just pause here to point out a wonderfully clear fossil of the evolution of the universe from a hot early state where it would have relaxed to statistical thermal equilibrium, and that would include thermal radiation with a very definite spectrum given only the temperature. The radiation would not go away as the universe expands. It would just cool by expansion. And here is the present evidence of a sea of thermal radiation very nearly filling space. Discovered independently by two measurements within a few months, completed within a few months of each other. John Mather and his group with the NASA Space Flight Center had a satellite, and even with their first few measurements, there's wonderfully small error flags. They can't be seen in this plot. Gush and all in Canada, University of British Columbia, and his two colleagues had similar measurements obtained at almost the same time. Each made the case independently that, look, this sure looks like, I remind you that the universe as it is now is transparent at these wavelengths. It can't have, as it is now, forced relaxation to this statistical equilibrium. That had to have been a fossil from a time when the universe was very different. But that's a dramatic result, well worth celebrating. These are iconic images, and the one quibble I have is that John Mather got a Nobel Prize for this spectrum, well-deserved, beautiful measurement, but Herb Gush got the respect of everyone who understands the subject, and then he moved on. Both sides handled this well. It's just, though, an evidence of the way astronomy science must work. Now, I want to turn to examples of multiple discoveries in the establishment of the hot Big Bang picture. And, you know, an immediate consequence is surely if there are multiple discoveries, there must be discoveries just missed. That notion grabs me a lot because I think today, surely there are multiple discoveries waiting to be made that have already been overlooked. So let's begin by introducing these four characters. On the left, Bob Dickey, my teacher when I was a graduate student. Next to him, George Gammage. Gammage was a refugee from Ukraine, Odessa, back when it was part of the USSR. He was an early refusenik, escaped to England, ended up in Catholic University in Washington, D.C., Fred Hoyle, and Yakov Zhdovic in the Soviet Union. Fred Hoyle in England, Bob Dickey in the US, both during the Second World War, worked at research laboratories, war research. Bob in radar development, Hoyle in radar application. Zhdovic ended up in the war working for the Soviet nuclear weapons program. Gammage was a real character, wonderfully inventive, a spectacular physical intuition, but accompanied by that, a lack of respect for the authority of people. I think in part that's why he was never involved in nuclear research during the war, even though he was an expert. By the end of the war, he was already working on the third edition of his book on nuclear physics. But his lack of respect, along perhaps with the fact that he was an expatriate from a part of the Soviet Union, meant he wasn't employed in that. So let us begin with a missed discovery. Here is Chandrasekhar on the left. Here, if I have it right, is Louis Heinrich. They, at the Yerkes University, this is a respectable powerhouse of research, particularly in astronomy. And here is a paper from Chandrasekhar and Heinrich, 1942. At that time, it was known that the temperatures inside stars like to be too low to be able to foster the formation of heavy elements. So where else could the temperature be high enough to produce thermonuclear reactions? Well, maybe in the early universe. They assumed that the early universe was hot, and they considered this reaction, which according to the Saha equation, if nu is a neutron, and one can use the Saha equation to write down the ratios of numbers of isotopes with successive atomic weights given the temperature. Now, they didn't say this, but in fact, this equation should be written thus. It assumes that you're in a sea of thermal radiation at temperature T. They don't seem to have noticed that, although surely they understood that they're assuming a sea of thermal radiation. And well, I think it does not seem to have occurred to them that as the universe expanded, the radiation would cool, but it would not go away. It would still be present and, for all you knew, observable. That point seems not to have been made. Here is a paper by George Gammage with his student, Rolf Alpher, and added to complete the first three letters of the Greek alphabet, unknown to Beta, Hans Beta, his name on the author list. This paper is widely cited, and rightly so, I think, because it is a pioneering explanation of what might have happened during the dense early stages of expansion of the universe. Gammage's main point: you shouldn't assume thermal equilibrium the way Chandrasekhar and Heinrich did, and others, because the early universe would have been dense, so it would have been expanding rapidly. And instead, you had better look at rate equations for building up of the elements. It's often not noticed. In fact, I haven't seen any author but me who has noticed that the theory presented in this paper is wildly inconsistent. Here it says, here are the two papers that Gammage wrote, published in 1948. Here's the first on the left, and here is the parenthetical remark, thus we have 10 to the minus 4 and not 10 to the plus 4. As given incorrectly in the previous paper, that's alpha, beta, gamma, because of a numerical error in the calculation. That wasn't a numerical error. The nuclear reaction rates they assumed were wrong by some 10 orders of magnitude. But it was not in Gammage's style to say such a thing. The past is past. Let's get on. Let's do it. And he did in this paper and followed up in this paper and reached a conclusion that knowing sigma v, the reaction rate constant for the capture of a neutron by a proton, which you got from beta, knowing the temperature at which the Saha relation would allow the buildup of deuterium, which at higher temperatures would be destroyed by photodestruction, and the onset of that stop of photodissociation is quite abrupt. Knowing the temperature and knowing sigma v, you only need to know a number density to get a reasonable abundance of buildup of abundance of deuterium. And Gammage never said it, but I guess he's got to have understood once you have the deuterons, then particle exchange reactions can go much faster because you don't have that fine structure constant slowing down radiative processes to build heavier elements. The key point, he knew a characteristic density that had to be true at about 10 to the 9th Kelvin if you wanted an interesting production of heavier elements. It was his student Alpher with their colleague Hermann who pointed out that if you extrapolate adiabatic expansion from these conditions to the present temperature at an estimate of the mass density at the present universe, quite uncertain, of course, but you get to take the cube root of it, you get a temperature of a few kelvins. So that's the key. In Gammage's relativistic hot Big Bang cosmology, you expect first a sea of thermal radiation at a temperature of several kelvins, and second, a large abundance of helium prior to star formation. That is because Gammage first had convinced himself that hydrogen is known to form about 50% of all matter. That wasn't known, but it was a pretty good educated guess. There were hints at that time. And furthermore, Fermi and Turkovich at the University of Chicago had checked that in Gammage's picture, the expected hydrogen abundance is large, and that almost all of the rest of it would be helium. So we have these two signatures. Now let's look at how these signatures were recognized. To this effect, I show you this group photograph from a conference in Ann Arbor, 1953, on nuclear physics, on astrophysics. Some famous people here: George Gammage, Walter Baade was the premier astronomical observer at Mount Palomar Observatory as it was being developed. We see here Jeff Burbage, who will figure in this discussion. His wife, Margaret Burbage, was again a premier observer, he a theorist. They made a powerful couple. Here is Dawn Osterbrock and Irene Osterbrock. I'll mention Dawn. Here is Vera Rubin, whose name I will not mention, but she was influential in getting us to face up to the presence of what looks like dark matter. So let us carry on. 1958. I should say, Gammage spoke, of course, and although he presented a nutty version of his idea about element buildup, I don't know why he abandoned the theory of 1948, which is on the exact right track, but he did emphasize that he expected a lot of helium. Now, here's an article by Jeff Burbage 5 years later. A conservative estimate is about 10% of the total mass of the galaxy has been converted to helium. If that were converted in stars or some other way in the universe that is about as it is now, it would be a massive release of binding energy that is not observed. Maybe Jeff suggested this energy had been radiated away in violent explosions in the past. But of course, he liked the steady state theory that just had been introduced. And in that theory, nearby galaxies are a mixture of young and old. You ought to be seeing these violent explosions in other nearby galaxies. Not mentioned by Jeff is that this could be helium remnant from Gamma's hot Big Bang. Jeff was, as we see, at the conference where Gamow, in a somewhat garbled way, discussed this idea. I don't know whether Jeff attended Gamow's lecture or whether he came away unimpressed. But it was, as I say up on top, this is an example of a missed scientific discovery of which we're seeing multiple. Here again, 1958 also, a conversation with Martin Schwarzschild, here pictured, in a discussion in the Vatican Conference on Stellar Populations, the previous year, 57. Hoyle, the difficulty about helium still remains, however. Hoyle was quite aware that there is a difficulty. Martin, the evidence for the increase in heavy elements with the age of the galaxy supports the idea, I have added, of element formation in stars. People then knew full well that the oldest stars have low heavy element abundances, a clear signature of production of heavy elements in stars as they evolve and explode. However, Schwarzschild goes on, it does not necessarily mean that helium production occurs mainly in stars. Gammow's mechanism may work up to mass 4, helium. That is why a knowledge of the helium concentration in extreme population 2 is so important. Extreme population 2 is just the oldest stars with the lowest heavy element abundances. So what is the helium abundance in these old stars? If large, then surely it came from the hot Big Bang. If small, then surely it came from stars. At the time, it was known full well that planetary nebulae, which are stars that have exploded and are on their way to making white dwarfs, planetary nebulae are plasma surrounding the evolving star. They're material blown off the surface of the star. They're thought to be a good measure of what was in the star when it was made. And it was already well known that in the spectrum of the plasma around stars, the helium concentration is uniformly high, running around 30%. Let us return to that subject in a while. Let me see, where are we now? Oh, Don Osterbrock had been at Princeton University, advances in theory of stellar structure and of the structure of the sun, in particular with new data on heavy element abundances, led them to conclude that the heavy element abundance in the sun is around 30% by mass. They observed that the same was found in studies of plasma in the regions around galaxies where the temperatures of the stars are high enough to have ionized the interstellar gas, again, a high helium abundance, and then in the relatively old sun, a high helium abundance. This can all be understood, they wrote, without difficulty on the explosive formation picture. That would not mean a lot to many people, but there is a footnote. Gamow, one of his relevant papers. Osterbrock and Rogerson had a Nobel laureate in their grasp, but they had other things to do, and nobody else seems to have noticed until recently. Why does this not want to advance anymore? Oh, okay.
It does advance for us.
It advanced too far. Where am I?
Yeah.
Ah, there we are. Jeff Burbage.
Yep.
1962, in a review of the theory with Margaret Burbage, Willie Fowler, and Fred Hoyle, a theory of formation of the heavy elements, quite extensive, lots of data discussed and accounted for in this theory, but not much mention of helium abundance. In this review of that theory, Jeff remarks that there is a problem with the high abundance of helium. And he remarks, the bulk of the transmutation from hydrogen to helium may have taken place in the first few minutes in the expansion of the universe. It's understandable maybe that this didn't attract attention because it was a side remark in a long paper. But again, nobody else seems to have noticed. But again, it's a wonderful discovery to be made if only you grasp it. Here, Bob Adele with others, observing a globular star cluster in which the stars are thought to be very old because their heavy elements abundances are very low. It even points out here that, where it is, the oxygen abundance is about a 60th of the abundance in the sun. There was in this globular cluster a planetary nebula. The planetary nebula had a plasma in which you could see lines of helium and measure their abundance. And you found a mass fraction around 40% helium in this planetary. I asked Bob Adele about this. He said they did not fully appreciate the significance for cosmology at the time. John Faulkner, one of Hoyle's students at the time, argues that this Odell paper was key to leading Hoyle to recruit Taylor to write their paper with the wonderful title, The Mystery of the Cosmic Helium Abundance. Here is Fred Hoyle's paper with Roger Taylor, and here is the punchline. The universe had at least one high temperature, high density phase, or other possibilities. Fred just could not bring himself to accept that we were building an empirically based cosmology. He felt that the scales of length and time are just so large that it can't be done. It made him very suspicious of the hot Big Bang theory. And so this confirmation of a notion of a hot early universe was put in very close terms. Now we continue with multiple discoveries, this time of the thermal radiation left over from a hot Big Bang. Here is Andrew McKellar on the right with one of the instruments developed at the Dominion Astrophysical Observatory in British Columbia, Canada, who remarked on the observations of that there are interstellar cyanogen molecules. They're identified by the absorption of light from background stars. The spectrum of the light from the background star has an absorption line at the wavelength or frequency, resonant frequency for excitation of CN from its ground level to its first rotationally excited level. But the surprise was that also absorption was seen from the first excited level of cyanogen to the next level. Knowing the ratio of absorption strengths in the first excited and ground levels, you have an effective spin temperature, 2.3 degrees Kelvin. Remember, Alpher and Herman in their publication, well, I get 8 degrees, they get 5. It's within the uncertainties, which are considerable, it is consistent with the cyanogen measurement. The main point is they're both not zero. They're a few degrees. This first detection was recognized only much later, but it's important because we have Fred Hoyle's review of the Gammage's third edition of his book on atomic physics, nuclear physics. Nuclear physics, right, that's what he says. In this review, Hoyle writes this book is mainly concerned with, it's good stuff. Let all this be emphasized before the faults are mentioned. The main fault of Gammage's hot Big Bang theory was that it would lead to a temperature of the radiation at present maintained throughout the whole of space much greater than McKellar's determination. That's odd. Fred cannot have looked at Gammage's paper very closely. Again, a multiple in missed scientific discovery. Yet again, in the US at the Bell Telephone Laboratory, some 30 miles by air from Princeton University, engineers were developing means of communication by microwave radiation. Here is an antenna it is a reflector cone. Light comes in, is bounced off the surface down the waveguide to very sophisticated detectors which had noise properties that were well known. To make the measured noise received agree with the sum of the measurements of the noise produced, including sky noise, which they measure by tilting the antenna from the zenith down. So you're looking through more sky, and so you see more noise as the, I don't know, as a trigonometric function you could work out of the tilting angle, the angle from the zenith. Anyway, when all was summed up, they had to account for about 2 degrees excess noise. Where could it have been coming from? Well, they said it was probably side or back lobes. But that, of course, they knew full well was a fudge that was not justified by the design of this antenna, which very strongly suppresses background radiation. Testimony to that, perhaps you have noticed here and there, microwave boosters, 2 of these scoop antennas placed back to back so that incoming microwaves are detected in one of the antennae, amplified and projected forward in the other. If there were any side lobe pickup, that system would howl. It didn't. These things were known to be very capable of rejecting background back lobe pickup. But they had other things on their minds. They had other things to do. This remained a dirty little secret at the Bell Telephone Laboratories for 5 years. Meanwhile, in the Soviet Union, here is Yakov Zhdovic, who at the end of the war had started taking an interest in gravity physics, general relativity, and cosmology. He was perfectly aware of Gammage's idea of a hot Big Bang. That was kind of dangerous, you know, because Gammage was a refusenik. Zhdovic, working in the development of the hydrogen bomb, was in a delicate position. But you know, Stalin and Beria and others recognized that if they want to get these nuclear weapons that they so much desired, they had better let these physicists work as they would. They had then the security of their essential presence for nuclear weapons. So they could get away with things that other scientists in other fields couldn't. Zhdovic knew that old stars have low heavy element abundances. So, okay, those elements had to have been formed in the stars. He was under the impression that the helium abundance is low also, and therefore that Gammage's theory could not be right. Nonetheless, in his group were Igor Novikov and Andrei Doroshkovich, who pointed out that although a lot of radiation would have been produced subsequent to the Big Bang, there would be a background that might hinder detection of this leftover radiation. The key point was that this leftover radiation would have a thermal spectrum that you could expect, even if the temperature were a few degrees, would stand out above the ambient noise. He could have made the discovery, but he knew too much about nuclear weapons. He was not allowed out of the country, and indeed was not allowed to talk at any length with an astronomer from outside the Soviet Union who would know perfectly well that the helium abundance looks pretty large. So here is David Wilkinson in Princeton with me and Bob Dickey. Bob had decided, for reasons all his own, that a hot early universe would be neat. And he suggested that David Wilkinson and Peter Roll build a Dickey radiometer, although he never said that. Build it and see if you see anything coming from the sky. And he told me, I remember this so well, why don't you think about the theoretical consequences? Well, so Peter went off to education. David and I stayed on the rest of our lives, our careers, following Bob's advice. How he knew? Well, these things happen. Anyway, That led to Roland Wilkinson to build a radiometer. As news reached the Bell Labs of this radiometer, Arnold Penzias and Bob Wilson, who had been struggling hard to find the source of this excess noise in the Bell telephone receivers, microwave receivers, were at their wits' end. They had tried every possible means they could of detecting the source of this radiation, whether in the instrument or in the surroundings. They are to be congratulated and rightly presented with the Nobel Prize for refusing to give up the search for the source of this radiation. And we should add, their overseers, Bell Telephone, are to be congratulated for allowing them to continue this search. And furthermore, Penzias and Wilson are to be congratulated for complaining about their inability to account for this problem, this phenomenon, and complained until news reached them of the Dickey et al. Experiment that led to these two papers announcing a great new discovery. Maybe the universe is filled with a sea of thermal radiation, and maybe that's radiation left over from the hot early universe. There are many aspects of this. Well, I already showed you that, in fact, in due course, the spectrum was measured, showed to be thermal, and that surely is a fossil from the early universe. Here's another fossil. In a hot Big Bang theory, I don't know why I said cold dark matter. What I'm going to talk to you about now is work with Jerry Yu, my first graduate student. Here's Dave Wilkinson, here's Bob Dickey, on how the hot early universe would evolve as it expanded and cooled. In the early universe, and we are of course assuming matter is baryonic, the matter would be thermally ionized. The plasma and the radiation would behave as a viscous fluid because photons are strongly scattered by the free electrons, and the free electrons are Coulomb scattered by the ions, making the three act as a plasma with viscosity. At a redshift of around 1,000, when the universe was linearly 1,000th of its present size, the plasma would be, the radiation would be cool enough to allow the plasma to combine largely to atomic hydrogen and helium, and the radiation would then be freed. If there were small departures from exact homogeneity in the early universe, then each Fourier component would know that it is a pressure wave and would oscillate, as shown here. This is an oscillation at a wavelength such that the matter is free to move at recombination freely. If you chose a slightly different wavelength, you might have the mode going downward. And in between those two wavelengths, you would have a mode with zero amplitude. The result in the present universe would be a Fourier transform of the mass distribution. I take the square root for messy reasons. We shouldn't have done that. Anyway, it has zeros and it's oscillating. Here is another signature of a hot Big Bang. Multiples in scientific discovery. So 1960, 1970, in the 1960s, people were well aware of this qualitatively. It was computed and made definite by Jerry Yu and me, and I published in 1970. It was first observed by Percival and al. In 2001, 30 years later. Who knew? Here is their paper. Here are the acoustic oscillations. It was rediscovered by Dan Eisenstein in 2005. Here's their paper. Here's their prediction and observation. They are looking at the two-point correlation function across the sky, a two-point spatial correlation function. And you know that if you have an autocorrelation function that is a series of bumps, more or less evenly spaced, the Fourier transform would be close to the Fourier transform of a sine function. It'd be a delta function, a bump, and there's the bump, rediscovered. This is the way science advances, sometimes big advances, sometimes small, sometimes rapid recognition, sometimes much delayed. Here is the present situation, just to celebrate the solid curve the theory with just a few parameters adjusted. The data, spectacular. And here is the mass distribution in the matter distribution measured by the distributions of the large galaxies. Again, the same theory gives you the solid curves in both cases. The measurements in the galaxy distribution, much more rough because there are far fewer galaxies than there are photons, but it's there. And the wonderful thing with the same parameters giving the same good fit. I draw your attention to an interesting point. Here is our 1970 paper, zeros. Here is a recent paper, bumps up and down, but amounting to maybe 5%. That is because most of the mass in our universe does not interact with matter or with baryonic matter or radiation, so it doesn't suffer these pressure oscillations. It only notices the gravitational effects of the oscillations, which are tiny. I introduced this dark matter concept in 1982 to take care of another problem that was considered rather pressing at the time. The CMB, the microwave background radiation, is much smoother than the distribution of galaxies. How do you account for that? Well, the easy way, which I tossed out, not thinking that this is any more than just a trial, was that most of the mass is not suffering this oscillation. Most of the mass is dark, doesn't interact with matter. This is a separate, independent indication of that dark matter. We care a lot about independent evidence, as I say below, but I want to emphasize it. Recall Charles Saunders Peirce's comments a decade ago. We care about independent ways of checking data. That's our whole basis for arguing we have a handle on reality. Just to summarize, but I've forgotten how fast I'm going, and I got to move a little more quickly. I have actually only one more point to make, but it's something that I guess maybe overly obsesses me. We have seen the possibility of multiple discoveries. I like to put it, it shows that times are right for a discovery. I have found that historians and sociologists and philosophers tend to think that the notion the time is right is kind of naive. It's deeper than that, they say. But no, I think, doggone it, the conditions were right to discover the hot Big Bang. It took time, that's the nature of science, but it was discoverable by lots of lines of evidence. And surely we haven't run out of anomalies, curious things that, if looked at in the right way, would be seen to be something interesting, maybe to be seen by more than one group or person to be somewhat interesting. I offer an example of a potential case. In the lambda CDM theory, structure in the cosmic structure in galaxies and their clustering in groups and clusters develops in a hierarchical way. Tiny knots of dark matter with their baryons form, merge, the merged objects merge, the merged objects merge in a hierarchy, in a merger tree. This is a really influential concept. I count merger tree in identified in research papers in cosmology. Not all merger trees in all these papers are in fact merger trees of the sort I have in mind here, but I've checked most of them certainly are. And I count 327 papers in 2022 that use that phrase. I really can't believe that there are 327 new ideas in cosmology in 1 year. We tend to repeat, and we tend to follow the party line, merger trees. Oh, and just as evidence, here is the European Southern Observatory. They show this illustration of the merger tree. It's beautiful, but it sure isn't right. Consider. Here are images of 3 nearby galaxies. Here are numbers for the mass fraction of stars outside the disk around the galaxy. They are from a paper, Benjamin Harmson et al., who measured the stars around these galaxies using Hubble Space Telescope, painfully measuring, counting out the stars. It says that star formation surely was confined to the disk. For consider this illustration again. Or did I show it? Yeah, I did. Here it is. When two of these clusters, subhalos, move together, if stars are forming in both of the subhalos, then when they merge, the stars in at least one of the subhalos had to have been scattered about. They had to have joined a stellar halo around the forming disk. It seems unavoidable. What's required by the observations of these galaxies is that star formation had to have been almost entirely confined to just one of the subhalos, right? That, it seems to me, is an intuitive but clear prediction. Star formation was confined to just one of the subhalos. How could that have happened? I conclude that the merger tree is a social construction supported by theory but not observation. Nothing wrong with that. So was general relativity at one time. But this one seems really challenging. So I think I've run out of time. In fact, I've run a little, and I would like to pause now to entertain any discussions that might be. Oh, wait, I forgot. Well, never mind. But there is a point I really like by Robert Louis Stevenson. It's a child poem, but childlike wisdom is great. The world is full of a number of things. I'm sure we should all be as happy as kings. The universe is filled with a spectacular number of things. And we have a great pleasure of sampling them and continuing to learn how they work, all in the tradition of natural science. Well, thank you. And if I knew how to turn this off, I would. Phew.
Thank you very much.
Oh, good.
Yeah, thank you very much for a wonderful lecture. We have some time for a discussion. So if you would like to ask a question, please raise your hand and I will call your name. And maybe while waiting for some hands.
Let me remark that I am new. Pardon me. I have only recently learned that I'm interested in sociology. So all questions are very likely to help improve my thinking about this subject.
Okay, so Ji-Hoon, please.
Yeah, thank you very much for a very nice lecture and history, lessons that we went over. You were actually talking about at one point that we are towing the line. Could you elaborate a little bit on, what you mean by we are towing the line, and how do we actually, yeah.
Maybe you are confused by a colloquial expression. May I put it, we are following the party line. Is that familiar?
Yes, that's what you said. Sorry, I mean, that made it sound like that.
Don't you imagine? In my impression, a young person is under great pressure not to upset the apple cart by questioning the wisdom of the senior people. Am I wrong?
I don't know, but isn't natural sciences? We encourage our younger people to be more challenging and giving different ideas and stuff.
Yes, we certainly do. But if we are being responsible, we will also remind them that if they acquire the reputation of being highly controversial, they will have trouble getting employment. Am I wrong? Let me put it, though, very directly. I do not question the great success of natural science, and particularly of physical science. It's spectacular. And it's done often by asking uncomfortable questions. How else could we get quantum mechanics? But I'm also pointing to a fact of life, that we all are under pressure not to misbehave. And misbehaving means violating conventions, wearing your hair too long. I guess that's now passé. Wearing too many tattoos. Contemplating the steady state theory. Questioning whether the universe really contains dark matter. And you know, in the 1990s, I wrote a series of papers pointing out that I could invent other theories that would fit the evidence we had then about the distributions and motions of galaxies and the CMB that did not have dark matter. It annoyed many of my younger colleagues. I know this in particular because one bright young person said to me, "You're only doing this to annoy." I was pleased to be able to continue the excerpt from Alice in Wonderland, Charles Carroll, Alice, spank your baby when it sneezes. It only does it to annoy because he knows it teases. In fact, in the 1990s, I knew perfectly well that I was teasing, and I was having fun by pointing to the fact that you didn't really need this dark matter to fit the evidence. But of course, I was brought down to earth by about the year 2000, when the first measurements of the anisotropy of the CMB came in and started to show a big bump at around, 100 degrees. Wow. And things have only gotten ever more powerfully tested and confirming lambda CDM. I remain convinced that lambda CDM isn't the final theory.
WBW MAB?
Yes, Sam Ting has seen several anti-helium-4 particles in his
Yes.
alpha magnetic spectrometer, and nobody wants to speculate, it seems, on what's going on.
Oh, people do speculate on even weaker evidence than that. Yes. What do you say? Do you imagine that this might be perhaps traces of antimatter produced in the hot early universe?
That's the question. Where did it come from?
Right. Good question. I don't know. But with Robert Louis Stevenson, I say, wow, the world is full of a number of things. And one of them is detection of anti-helium. But you know, I am told that in nuclear collisions, yes, energetic collisions I have read of colliding proton beams that can produce anti-deuterons. Am I wrong? And I think they also can produce anti-helium in trace amounts, but who knows? I certainly don't want to give the impression that everything is settled and done with. We have things to learn from, including anti-helium.
Maybe I can ask a question. You told us about this multiple discoveries in the past, and I can imagine for us to look back, say 50 years ago, it's much easier to identify the missed discoveries. But let's say we try to draw the lesson for the present. So when we, in a much messier situation, what shall we take in our practice of science?
I think we're doing right, but let me notice a particular point. Much of research in observational cosmology today is confined to large groups that are building big instruments to make precision measurements of measurements that have been made before. That's entirely reasonable and sensible. We have learned from measurements. Let's do the measurements better. But there is the hazard that by looking only at questions raised by lambda CDM, you might be missing questions that would be revealed only if you thought about the universe in a different way. And so I think we should, and some do, spend time looking for odd phenomena, odd inconsistencies with accepted ideas that might be pointing us in new directions. I have mixed feelings about young people doing this. First, as Maxwell explained, you pour information into a young mind, you may get wonderful results. Or you may produce a student who has developed a bad reputation for crazy ideas. That's why I think it really behooves us of advanced age who no longer even have a salary to ask these questions. But I think certainly we should be recognizing that lambda CDM is a far from complete theory. And so we really ought to be looking around and raising awkward questions, seeking them out.
Thank you. There are a couple of questions in the chat. First, from Michelle. Could you please comment on the H-ARP observations against the Big Bang? It's a question from the chat. I can read it again, or? Sorry, Jim, can you hear me?
I hear you, and I think you are asking about what is known as the Hubble tension.
Well, maybe Michelle can unmute herself. I'm not sure. The question is, there is some person H-ARP, and I guess there are some observations against the Big Bang theory. I don't know if you...
Can you speak?
Yes.
Okay, if I'm not mistaken, Harold Harp has observed that distant galaxies having high redshift cannot be so far away. They should be close to us. He has made an atlas of all observation he has made. Thank you.
I do not know this author or the phenomenon to which the author is referring. To all I know, galaxies at high redshift are at great distance. That is, of course, an inference from limited evidence. So always it is right to ask, is that really so? To me, it's not a very attractive question because it goes against so much that we see. But it's a good question. We should consider it. It goes along with the question, if the galaxies are moving away from us as fast as indicated by the redshift, then the surface brightness of the galaxy should be diminished. It's a simple consequence of it's a simple consequence of Lorentz transformations. Distant, high redshift, fast recession, low surface brightness. That's observed. It really works out quite well. Doesn't fully answer the question, but if these galaxies at high redshift were really moving as fast through Doppler shifts as indicated, then they better not be very near or they'll soon be very far. They're moving so fast. If the redshift is due to something else, then you have the big question. How is it that the microwave radiation has been redshifted in just such a way that as it reaches us, it remains a thermal spectrum? That thermal spectrum is a prediction of standard physics, but it is nonetheless a prediction that is tested by application to a remarkably large-scale effect. This is radiation making its way from decoupling at high redshift, at redshift 1000, to the present, and maintaining its thermal spectrum. Wavelengths increased, energy decreased in just such a way as to keep the spectrum thermal. That's a pretty impressive result to me.
So there is another question from the chat by Tuli. Would you like to unmute yourself, or shall I read it? So,
sure, I'm happy to unmute. So
please go ahead.
Thank you, Alexander. So, Jim, I'm interested in the conditions where discoveries can be made, and I found it interesting the cultural and sociological aspects that you were touching upon. So my question is really, what kind of context, what kind of different context can you imagine where we could make discoveries that are outside of our current reach? You referred it to a little bit, like maybe some questions can be better discovered in a situation where we don't have salary and we can, our career doesn't depend on that. I wonder if you have more thoughts on that.
Thank you for putting me on the spot, challenging me to say what I mean. I look at the past and where we recognize the many discoveries that were absolutely startling. One, that the Earth is not in the center of the universe. That the solar system is not at the center of the universe, the stars in our galaxy, and that the stars in our galaxy are not at the center of the universe. There is no center. That Maxwell's equations fail if you apply them on the scale of length and energy of an atom. Startling. And that you have to introduce the uncertainty principle, a shock. I don't pretend to predict that there will be more discoveries on that, to that extent, but I certainly don't rule out the possibility. Just to throw this out, we have known there have been efforts to reconcile the quantum and relativistic principles since the two were discovered. Lots of work. I guess it's close on a century of research has not revealed what you and I might consider to be a sensible reconciliation of the two principles. One possibility, we're just being stupid. If we had the right imagination, we would find it. That would require, I expect, looking in an odd direction. Maybe the odd direction is superstring theory. I don't know. It's been advertised, but it's hard to see concrete results. I hope I'm not wrong about that, but it seems to me it's an open question. And maybe the answer requires another shocking discovery. Just to throw it out, because I've learned to be, you mentioned absence of salary. Well, I'm being a little skeptical there. I'm not complaining about the absence of salary. And I'm grateful for the freedom. I don't think you have to, if you have a salary, you should be still free to ask these questions, but be careful, a little careful. How do we know that nature operates by rules we can discover? That was never issued as a guarantee. It was made up as a thought, a positive thought. How do we know that there is a connection between the two principles, relativity and quantum? It would be a shock, but, well, we have to consider that possibility.
Maybe last question, please, Chris, from the hand up. Chris Quigg, yeah.
Hi, Jim. It's Chris Quigg. It's good to see your face even on the screen. Let me start by endorsing your book to my colleagues. It's really a wonderful exercise for somebody like me who is a little impatient with sociologists or philosophers to hear your take on it. You started your talk by talking about general relativity as having once upon a time been socially constructed. And you've just talked about a little open-mindedness with respect to lambda CDM. Or anything else that you'd like to cite at the moment that has the status of a socially constructed theory that we might try to validate better or rule out? Thanks.
Would you accept superstring theory?
Whatever you say, sir. I
It's
was
good to
thinking
hear.
perhaps of inflation.
Yes, I would agree. Inflation is a social construction. We don't have many alternatives. Paul Steinhardt is to be congratulated for introducing an alternative. Neither inspires deep confidence in me. They may be simply made up stories, or who knows, maybe one of them is right, or maybe aspects of the two are the right direction. We just don't know yet.
What about the standard model?
That's not in my hands, luckily. But surely, well, again, no one issued you a guarantee that you could rationalize the standard model, put it all in a package and account for the values of the constants. And you've been looking for that standard model for quite a long time. Why the lack of progress? No criticism, but just a question. Are we guaranteed that you can build a more compact, better theory of particles?
There is another question from the chat regarding, I guess, the status of MOND versus dark matter. What is your?
So if we did not have the tests I mentioned, but we knew that MOND, as introduced by Matti Milgram in the 1980s, now matches wonderfully well the relation between the circular velocity of the stars in a spiral galaxy and the baryonic mass of the galaxy. If we had known that, but not all of the other evidence, then I would have said, yes, the best option, the best picture for gravity on large scales is MOND. It still has that one successful prediction, but I put it against the spectacular variety of tests that lambda CDM successfully passes. And by successfully, I mean, let's be charitable. No one has asked me about the Hubble tension, but I will just say it's a 10% anomaly, if real, in the comparison of a parameter that is devised in two ways, one of which depends on what's happening now, and one at redshift 10 to the third, 1,000. That an extrapolation by a factor of 1,000 in expansion introduces a 10% error, I'd say, wow, that's pretty good. That's pretty precise. It's not perfect, and so if real, it shows us that lambda CDM can be improved, which is even more interesting, very exciting. So, MOND, I think, is not interesting, in my opinion.
Okay, well, I think we already half an hour through the end of the talk, so we would like to thank you very much again for the wonderful lecture, and everyone for joining today. Yes, and thank you very much, and goodbye, everyone.
It has been my pleasure.
Thank you very much.
Bye-bye. Thanks a lot.